So we're going to stick right now in the field of medical robotics. And now we're going to hear from Alon Wolf. I'm sure many of you already know who he is. Alon completed all of his degrees here at the Technion in mechanical engineering. He went on to do post-doc work and work as a lecturer at Carnegie Mellon, also in the Robotics Institute. We have a strong presence here today. Alon is the founder and director of the Biorobotics and Mechanics Lab, BRML. And of course, he's the vice president for external relations and resource management, if I'm correct. So without further ado, once we get this set up, Alon Wolf.
Thank you, everyone, for inviting me, and I want to give you a very short, selected review of things that is happening in my lab, which is in the mechanical engineering department, the Biorobotics and Biomechanics lab. As was mentioned, I'm got all my degrees here, and I'm a faculty here since 2006. My work, and this for these of you mechanical engineers, is focusing on kinematics of mechanisms. So if you remember the course that we give in our department, focusing on screw theory, line geometry, and all kind of topological maps of mechanisms. And then I apply it on robotic devices, some of them flexible, some of them less flexible. In the last 15 years, also working very strongly on human biomechanics, gait analysis, and working with collaboration with the Israeli Olympic Sport, with the Israeli Olympic Committee as the Israeli Center for Olympic Sport Research. And I'll talk also about Helping Hands, a philanthropic activity that we do out of the lab, and many students are involved in this activity. For those mechanical engineers, you probably remember from dynamics what screw theory is or screw motion is. So we use this to do analysis of mechanisms and topological maps, line geometry, screw theory, to understand the theory behind designing of mechanisms. So this is the theory behind the practice that you're going to see, but I thought I would put two slides, no algorithm, or excuse me, no integrals, no differential equations here, just the output of what you get. After you do that, you go and design robotic devices. And I'll show you some of those, and thank you, Owen, for giving me an intro on surgical robotics. So this is a robot that I designed in 1998 during my PhD with Moshe Shoam. And this is a robot for spine surgery. It's called Spine Assist. It's a small robot that is attached to the spine, to the vertebrae, and guides surgeons to put screws into the spine when there is a need for spinal fixation. Here you can see a CT of the vertebra, and the robot is attached here, and it's putting the screws here. For those mechanical engineers, the tolerance there is less than 1 millimeter. And the consequence of putting the screws not accurately is just penetrating this area, which is the spinal cord. According to literature, 10% of the screws will get into the spinal cord. Minimal amount of screws you put in a surgery is 6. Surgery is done virtually first, as you could see. The surgeon is designing the surgery on a virtual environment of the patient, CT and MRI scans. And then during surgery, after doing what we call registration procedure, the robot is executing very accurately what was pre-planned on the computer the day or a few hours before surgery. This robot is FDA approved. Moshe did a company called Mazor, very successful spin-off company from the Technion, and has been operating worldwide in the last 20 years, putting hundreds of thousands of screws worldwide, zero mistake, meaning that there are tens of thousands of people around the world who walk who are not supposed to walk because of, you believe, the statistics of how many screws penetrate the spinal cord. So this is a classical example of a medical robot or a surgical robot is operating out there in the field, output of the Technion or the mechanical engineering department. I was mentioned, I moved to Carnegie Mellon, to the Robotic Institute. Pittsburgh, where Carnegie Mellon is very famous for Carnegie Mellon, also very famous for ketchup. So for those of you who love Heinz ketchup, this is produced in Pittsburgh. But I got there right after 9/11. And this was the first time where the American search and rescue teams tried to use robotics to try to allocate survivors under the buildings in New York, also in Washington, instead of risking the life of search and rescue people, although more than 400 died there, I think, during 9/11. And when we were asked to develop robots, this is 2002, this is the kind of robot we came up with, an elephant trunk-like, or an extended, a very flexible robot, 20 degrees of freedom, or 20 motors here, and the robot has sensors embedded, and it extends the reachability of this hobby car that we bought in Toys R Us, but just to show that you drive and then you deploy a flexible arm and you can reach locations which are not in a linear trajectory. This was the work in 2004. At some point, we took these robots and disconnected them from the base, and this was already done here at the Technion, and the result were snake robots that crawl and roll within the lab. They're untethered, they're fully controlled by algorithm embedded in the snake itself. Computation is on board, energy, communication, everything is on board. This was printed in 2007 by Object Technology. We were test bed here for Object, so we had all their printers. I think this is probably one of the first robots in the world that were printed, 3D printed in 2007. It was displayed in Expo in Germany. Now to build a robot is easy, but how do you control them? So to do that, we brought live snakes to the lab. We have a motion capture lab, and we did gait analysis for snakes, trying to understand how snakes locomote. And we did hundreds of hours of recording, and then did reverse engineering of their motion and tried to copy it. Now, here is some calculation, but if you take, and you heard the expression here, configuration space, you take the amount of possibility of 20, let's say 20 motors in a robot, all the configurations per step to make the robot move from point A to point B, you reach up with a search space which is 10 by the power of something, 3,000 and something, which is something you cannot solve. By the way, the number of atoms you see when you look in the horizon is 10 by the power of 80. So you can imagine what the search space is here. So you have to take some assumptions. And there are some assumptions you can make. Of course, the snake cannot be here and then jump over there. There should be a continuous motion. But nevertheless, it's a huge, huge problem. So what we came up with is creating, we didn't call it digital twin yet. I was not smart enough to patent this. But we did a dynamic simulation or simulator of our snakes on the computer, as close as possible to reality, with friction, with the dynamics, everything. Once we had a dynamic simulator of the snake, we validated it by giving the real snake and the simulated snake the same motions, the same commands, and then tracking, you see those those spheres, we track those with the camera system we have in our lab, and we try to validate the arrow and how accurate the two snakes are. I mean, our dynamic model versus the real snake. We reached 65 to 70% accuracy. In 2008, it was quite nice with the sensors that were available. Today, companies reach 90% accuracy, and it's called digital twin, to have a digital twin of your device, of your car, or of your robot, of your process, your factory, everything. And what do you do with that? So now we have a computer animation, or not animation, dynamic model of the snake. Then we use genetic algorithm to teach the snake in the computer to move, with the theory that the motion that are developed on the computer, because you can evolute them very fast, you can do on the computer millions of evolutions very fast, copy them to the real snake. So using genetic, I don't need to teach you here in computer science what is genetic algorithm, with all the mutation and all kind of taking few successful motions, creating a third successful motion, giving an objective function, good motions remained, bad motions were extinct. The genome, the cells, were the motor commands that we were sending to the robot. And after running, my students was able at that time to take over all the computers in the computer farm in the mechanical engineering department during the night. He was at a Tudai, so he knew how to do that. You end up with motions that were created. And then you take them and you copy them to real snakes. So these are the real snakes, the robotic snakes that execute the motions that were developed in the computer algorithms. So you see them rolling, crawling, standing up, climbing up stairs, and all kind of crazy maneuvers. Again, 20 degrees of freedom. They can break, they can split, they can do all kind of cool stuff. Now, remember I started with medical robotics. So, and this is related to the previous speaker. Minimally invasive, I don't need to talk about this because it was already explained that if you want to do a minimally invasive surgery, you need to have a direct line of sight between where you enter the body and when the point of interest is. If there is something blocking the way, it's very hard, given that you're operating with something which is very rigid. So with that in mind, we came up with the idea, let's take the snakes, which we had for search and rescue, which are good for elephant minimally invasive surgery, and try to shrink them down a little bit to something that can be used on humans. And Amir Dgani is here. I see you, Amir. Amir had the honor to be one of Amir's advisors in Carnegie Mellon. And Amir, you recognize this, I guess. This is your prototype. This robot was, this was the first prototype of the snake robot, which is about 10 millimeter in diameter, was about 40 centimeter long. By the way, won the best paper in Biorob at the IEEE, if you remember, Amir. And then this is a company was established, and this is the result, Medrobotics. It's the first ever robotics system that was approved by the FDA as a surgical robot, and it's operating now worldwide. The idea is we call it follow the leader. The head of the snake has a stereo vision, and the snake just follow where the camera goes. Imagine a free-flying camera. The rest of the snake just follow where the trace of the camera is. It's based on two concentric snakes. One is rigid, one is flexible, and we're playing there with cables and all kind of sophisticated algorithms. And at the end of the day, this is what you get. You get a snake that drives deep into the body, and then through the snake, you perform surgery. As you can see here, driving the snake inside, removing. This is the first ever scar-free surgery performed by George Washington University with this system, removing a tumor in a place you could not reach before unless it was an open surgery, and then you even suture. Now, this is the snake driving inside the body. The head goes, and then the rest of the body of the snake just follow the leader. More work related to medical robotics is this work about knee replacement surgery. Today, the surgery is performed with the jigs that helps the surgeons where to cut, but with the new generation of implants that look like this, these are cartilage that is grown in a plate in a lab, the geometry is unknown. So, and this is how it's being done in surgery. It's freehand sculpturing. So what we did is we designed a robot that is attached again, like the spine robot, to the anatomy. First, it scans the anatomy that it needs to operate. It collects data from the surface of the anatomy. So you create a surface, and then you replace the scanner with a burr, and the burr is now machining, 3D machining the surface of the bone, preparing it for implant. Now, the new generation of the robot that we have now in the lab is replacing the burr here with a 3D printing head, and now you deploy material. You deploy plastic or you deploy biomaterials that will be, at the end of the day, an artificial cartilage. So we call it all-in-one, by the way. All-in-one, you scan, machine, print. I mentioned that we have I brought some toys here, so I forgot. So I spoke about the snake robot. So here it is. Okay, so you hear the motors? Okay, so this is the snake robot. Everything is inside, computation, communication, power, so it's untethered. And you're welcome later to play with it if you want. It doesn't bite. Last time, yeah. And we also have, tell you the story one. We also have a very big gate motion capture lab, I mentioned it, with camera system in the circumference of the room that track motion of objects. Whatever we want to track in the lab, we have other sensors like electromyography for muscle activity and force plates, etc. the markers reflect back the light that is emitted by the camera. By the way, it's the same technology that Hollywood is using to do all those animation. We buy them now in eBay after we know that Disney's released a new video. We look for the cameras, we buy them for 10% of the value because they sell them after each production. But as I mentioned, we work with the Olympic Committee, so let me show you what we do in this sense. So this is the European champion in Israeli. She's an Israeli weightlifter, and she is here in the lab and 80 kilograms. Quite impressive. Now, watch that she's censored. She has all the markers on her, and we measure her muscle activity and her motion. This is very technical, and here every tip you can give her can mean a medal and no medal. And this is the reconstruction that the system is doing from the weightlifting. So you can see the weightlifting. You see those red arrows are the forces that she applies on the floor. Very easily, you see she's very asymmetric. So we give her feedback and we help her. And so this is another kind of branch of activity that comes out of the lab. But let me go to the last part of my talk, and this Helping Hand project. We are designing, building, putting together, and giving away prosthetic hands printed to children all over the world for free. It's a project that started with two of my PhD students, Yair and Shunit, and with a collaboration with Haifa 3D, and here it's a good point to recognize Dr. Yoav Meidan, Zichrono Livracha, that was a big collaborator on this project, and this is an evening on his memory. Many, I think, know him. He was here on campus. He was one of the collaborators in this project. With the idea of this project is to replace the existing prosthetic hands that you can get. You can either get a hook or something which is very expensive. Very expensive is something like this. By the way, we got it from an Israeli soldier, Patsua Milchama, that gave it for free to us because he's not using it. He's using our designs. And the reason why we're doing it is because this kind of hands cost something around $80,000 to $100,000. Or, you see the order here, tens of thousands of dollars, something that children cannot afford unless you're born to the right parents. And just to give you an idea, each motor here, which are from Pitman, is about $700. Now, the hands that we are designing are limited to maximum $100 per hand. So you can print it and do it everywhere in the world. It's all freely available. So this is Dean. Dean is doing his master's and now PhD with me and Alex Bronstein. Poor guy has to satisfy 3 professors. But what we started with is doing some kind of an analysis of how the hand work. And you can see in the 3D gate lab, you can actually identify the fingers working. And because he has the markers here, and we measure forces and etc. And then we designed the entire pipeline from 3D scanning with low-cost cameras, the RealSense by Intel, from Ronnie Kimmel from this department, creating the CAD models to the deformable CAD models, printing, and then controlling the hand, and then giving it away. This is a hand tested in a lab. You can see it's picking up an egg with a robot and doesn't crush it because it has force sensors. It detects the forces that it applies on the environment, and it makes sure not to crash the egg. Now, a very nice work by Shunit was this reach to grasp idea. So when you have a prosthetic hand that looks like this for the children, by the way, you can any color you want, logos of football, everything. That's the fun part. It bears a psychological burden on the operator to reach, open the hand, orient it, close it, things that we do automatically. So what Shunit tried to do is with wearable sensors to bridge this, we call it, to understand what we want to do, where the prosthetic hand should be automated. And I'll show you exactly what she did. You see, she's using all these kind of inertia sensors, accelerometers on her arm, and she collected data And then using advanced kinematic tools, she broke down the data to the very principle of the motion. And using, again, artificial deep learning system, the system learned the reach to grasp motions. So notice that the hand is closing, kind of grasping, when she's doing the reach to grasp, and she's about to grasp an object. She cannot wear the hand, of course, because she has her own biological hand. But when she does, she talks, she moves her hand chaotically, the hand will not respond. So the algorithm was able to detect those principles of the components of the motion that define a reach to grasp motion. And this is now implemented in the hand. And another project I would like to show you is by Dean. I don't know if Dean is here. Dean is not here. Dean is actually... Oh, Dean! Where are you? You're here. Yeah. With Oren again and with Alex, and Dean is doing a phenomenal job, don't blush. And it's the first time ever in the world, I guess, Dean, that a robotic hand is operated with ultrasound, real-time ultrasound. So here is an ultrasound device, you see the image, the system learns with, again, deep learning, the motion of the muscles that you would see here, and then make the hand work and the dexterity, so we detect fingers, the intensity, and in real time. Oh, you didn't hear the music. Let me do it again. So, in real time, analyzing the ultrasound and then operating the hand. So this is another project, a collaboration between computer science and mechanical engineers. The hands were given to many children around the world. As you can see here, some of the prototypes. This is Ben Spitzel, the soldier I told you is the most wounded soldier in deserts in Amud Anan. And you see, by the way, this was a bug. It sounds like he was British, but drinking the tea, but it was a bug. He's actually laughing a lot, but he's using one of those hands. And these are some of the children that are using those hands. The last thing I want to show, by the way, we got the Variety Award this year for this activity, and we're very, very proud. The last thing I want to share with you is a collaboration, again, with Lee Tselnik-Mano from Electrical and Computer Engineering. And it's relating to tactile feedback. Giving a full, the metaverse, everything is about virtual reality, but what about touch? Can you touch object and also sense the texture? So we were able to design the first device in the world that gives you texture sense. So you can touch and sense a texture of a fabric or something and taken from an image. And this is the work from Lihi.
Imagine being able to touch and feel virtual worlds. We are a team of researchers from the Technion, and our aim is a complete immersive virtual experience combining multiple senses. Today we can see and hear remotely. So what about touch?
There's different textures in this sweater.
Most of what we do in the real world relies on tactile feedback that is perceived through mechanoreceptors in our skin. Holding a glass of water, putting on a shirt, all these daily actions rely on our sensation of touch. Bringing this technology to the virtual world will be a game changer in a plethora of applications.
The reason you don't see me here because I was in public. So I was sick at home. Thank you. If you have any questions, of course.